So as I was saying that, that we can remodel, like initially we may start with more variables and later we can drop some of the variables which are not significant and we can do a respecified model, right? So I have already uploaded this paper on the Blackboard. You will see that they have a folder, so you can access my paper in fact. So let me show you guys, like this was like a cross-sectional data and I mainly used the World Bank datasets, 185 countries, okay, and it was, I think the base year was 2013, so I did only for 1 year, okay. So cross-sectional, so it's a very simple model. I wrote like a half page of abstract in the beginning, so this is what I also want from you guys. So choose a title, write your name, choose an appropriate title, name and the university. Then half page should be like an abstract, so that will give a summary of what you're writing about, so that I know that okay, you're talking about these things. So the introduction I wrote like two pages, 2.5 pages. Then I wrote like whatever literature review I did in section 2. So literature review would be also like 3 pages roughly, okay. So after the literature review, you should talk about the analysis part and the data, like where you got the data from, which year you are using, how many countries you are selecting, so on and so forth. It's not necessary that if you select more than 100 countries, you don't have to list the names of all the countries here. Just mention that I have selected such and such number of countries from Europe, North America, Asia, and Africa, and so on and so forth. Then after you described about the data in the analysis part, you should discuss about the variables part, like what are the variables in your model, okay. What's the dependent variable, what's the independent variables that you are selecting, okay. I'm expecting you guys should have more than 4 independent variables at least, okay. Don't just do like one independent variable and one dependent variable, then it's like a simple regression model. At least 4, I mean, independent variables, right? Then part C, in the analysis part, you should write your model. You should also like shorten the model in like a readable format, okay. Don't write like ln of total health expenditure equals to, because that would make the equation very big. Shorten it using abbreviation and then later maybe describe what those stands for, okay. So after you did that, you should mention how you taken into fact of the multicollinearity problem. You have to do a variation inflation factor test, right? So I have stated that that's how I kind of eliminated the possibility of multicollinearity, because the VIF was less than 10 in my case. In fact, VIF was less than even 5, so it's not multicollinear at all. So I can do a simple like multiple regression model, right? Then you also have to say, because it's a cross-sectional data cannot be homoscedastic, right? So it can't be homoscedastic, so we have to use the heteroscedasticity test. So I did the head test, and that also suggested that the model is not heteroscedastic, so it did not reject the null. Null is homoscedastic, right? And the thing that I was talking about, that initially if you see, I have 1 2 3 4 5 independent variables, right, in my model. But one of the independent variables was not significant, like ln of lit. I dropped it and respecified the model too, okay. So you can do that as well. In fact, today's class we learned that you can drop some of your insignificant variables from the model, right? It's, if you go back, right, So if a variable is statistically insignificant, one may think of dropping it from the regression. So we can drop the insignificant variable. Okay, that's exactly what I did in my paper. So if you guys have chance, take a look at my paper, like how I have written it, how I taken care of multicollinearity, taken care of homoscedasticity, and so on and so forth. So I did like VIF test, I did head test. So that's the analysis component, right? So that was like after analysis, then you talk about the results. Since my model is, all of them are like log-log model, and my health expenditure model, if you also look there. So log-log, the advantage of log-log model is the coefficients are the elasticity, right? So I directly got the elasticities for all my variables except fertility rate. You may ask why I didn't take log of fertility, because fertility rate is from 0 to maybe 8 or 9, right? Like an average fertility rate of each country. No people is going to take like more than 9 kids, like at least in this type of period. So if I take log of that, log of 10 is like 1, right? So it will make it a very small value. So that's the justification why I didn't take log of fertility. You could have asked, like, if you use log of fertility, it's easier to calculate the elasticity, right? For a log-log model. But that's why I avoided, but there is a mechanism how you can calculate the, even if it's not the log-log form. So the formula is e to the power beta minus 1 times 100. Beta being the coefficient of the fertility model. Right? So if your independent variables doesn't have log and your dependent variable have log, you can use this formula to calculate the elasticity of fertility. Right? So that's how I did it. And then after the results of after the analysis component, I criticized my own paper. Like, what are the shortcomings of my own paper? So like I did not have like I had missing observations for some variables, did not have enough information. Then I could have I wanted to analyze using like other explanatory variables like drinking. Unfortunately, I didn't have data for that. My R square for the model was somewhat smaller. It's 0.349. Okay, it explains like 34% of the variation of y given the variation in x. So it was somewhat smaller, but it doesn't necessarily mean that with small r square you cannot write a paper. You can still write a paper, but I would have loved if I could have added more explanatory variables in my model. If you add more explanatory variables in your model, the r square value increases, but that doesn't mean you add any nonsensical variables that doesn't make sense, right? So I explained it pretty nicely in my paper. Like if you have a chance, please read through it. The critic part, I also criticized that I did not use a panel model, because in a cross-sectional model you cannot capture the time varying effect, right? Because every year everything is changing. Like that way you can capture the time varying effect. Like maybe obesity in the United States is going down, maybe smoking is going down. In fact, smoking rate or people smoking publicly has gone down, because the states have implemented policies that you cannot smoke in public, right? So especially in universities, like in academic settings, or they have like state laws, or sometimes like at a federal level as well. So if you use a panel, the power of panel is it can capture those effects, right? Panel is really powerful. So if you are I have in fact taught applied panel in the Stata class, right? Watch the video, it's already up on YouTube. So But if you are like short in time, you don't want to do a lot of cleaning, you can start with a basic cross section. Okay, for this course, cross section is enough. Okay, I'm not expecting that panel, but although I taught it, I mean, in fact, I was not supposed to cover so many things in the class, but you can read the conclusion, like a lot of suggestions, policy suggestions. The references are really cited nicely from the Google Scholar, right? Last class I showed you guys how to use the cite function from the Google Scholar. You just click on the cite function, it will cite it in APA style. Okay, choose the APA style for. I prefer the APA style citation. They have Chicago style, they have MLA, but APA is the best one. Okay, it's like very neat and clean, looks like very professional layout. So I have like 28 references. I read a lot of papers for writing this paper. I would recommend you guys to at least have at least eight citation at this level. Okay, I did like 20 something citations. And then I attached an appendix. In the appendix, you should have the results from Stata. You can do that by print screen. Okay, print screen and capture your results, and you should have the table form, like, so that I can see that the results are consistent with your analysis part. I also want you guys to submit your do files. Okay, this is the first time actually I'm implementing this strategy, so that I can see that whether the results come up or not. So submit your data file and the do file. Okay, and use the Stata like labs in our econ department. You can go any time of the day, they will give you access because you're taking the course, right? So go to the econ lab, use your Stata. It might take only 2 or 3 days because I have eased the process of cleaning. Okay, previously when I wrote this paper, I myself didn't know how to clean the world of data set. Okay, I have figured it out. The best method is like if you rearrange the data set from the variable list, right? Like I have arranged like properly, like that if the country should be in row or column, or the year should be in, because if you just download it by default, the cleaning process itself will take 2 weeks to clean if you just follow the default format. Many of our students are just downloading the default format. In fact, even the graduate students, right? So they struggle like 2 weeks, 3 weeks. But I have made it easy. I told you guys, select time as series or country as rows or columns, or the variables as, so it comes as in a format that we want for our analysis, right? You can also produce the normal table. So when I did like log of all the variables, I actually typed histogram, and when you type histogram of the variable, it will give you a normal distribution curve. So I can see whether your values are normalized or not. See, the fertility variable is actually not that normal if you look at it. Okay, so this is one of the critique in my paper, that I could not use log of fertility because the fertility values are, the extreme value is 8. In fact, it's lower than 8. So if I take log of 8 is like 0.0 something. So then the regression result won't make any sense if I log it. But it's not normal also. So that's one criticism of my own paper. So if I criticize my own paper, that means I knew the problem and I stated it. So if you are submitting your paper in the journal, they will know that yeah, you knew the problem. It's not like they might assume, if you don't write the criticism, they might assume you don't know about it. That's why you didn't take the log, right? It would show that that person doesn't have any knowledge, like he doesn't know. Maybe that's why he didn't log it. But I explained that because of these problems, I could not log the fertility rate, because the highest value from the histogram, it shows it's 8, right? But all the other variables are kind of normal and centered, because I have used log for all the other 5 variables. I also tested the omitted variable bias. In fact, I forgot to give question number 5. I wrote what's omitted variable for bias. Okay, but unfortunately, when I was like printing from home, my printer was not working and I didn't save the quiz file. But you can also check if there is like omitted variable bias in your model. You can do a OV test. Okay, so you can read my paper for the OV test. Okay. I have written the table in a very clean form, so you can see all the details. Right? And for my panel paper, I did not give out my panel paper to you guys because it's not a part of the requirement of this course. And but I have given the presentation slides for my panel paper. Okay, the presentation slides actually is from my panel paper. Right? Where I used like an instrument variable. Right? So you guys can so this is a very useful advice, like dropping some variable and making it. Okay? But if the sample size is small, effects might be imprecisely estimated. So you have to make sure the sample size is big. That's why I took the number of countries as much as possible. Those are the number of observations in my country. Like how many countries you have and the number of observations. Right? So in a multiple regression setting, we can also do like a confidence interval. So if you see that the estimated beta hat, the negative, this C0.5 is actually the critical value at the 5% level. Alright, so it's critical value at 5% level is typically 1.96. Oh, sorry. So 1.96 times the standard error of the beta hat. Okay, you can also say that when you estimate your model, you can also find confidence interval that within 95% confidence interval, like let's say you estimated like I estimated like if there is an increase in like how aging population, the cost of, let's say the cost of each additional children in the United States is roughly like 8% of the GDP, almost, okay, per capita, not GDP but GDP per capita, 8% for cost of each additional children. And from my model, I found it was like 11%. Okay, so it was slightly off the chart, but still it was pretty close of the, because the fertility rate coefficient is the elasticity of that came out to be 11%. Right? So that you can use a confidence interval and say that, yeah, that the 11% that you predicted may lie within, if you do a confidence interval, you will get the lower bound and you will also get the upper bound, right? So maybe that 11% would lie maybe from 9 to 13. Okay, provided that the standard error is like close to 1, or if it is lower than that, then those values will be closer to the estimated values. All right. So the bounds of the interval are random. In repeated samples, the interval that is constructed will cover the population regression coefficient in 95% of the cases. Okay. In fact, we want a smaller standard error. Smaller standard error, that means our estimated coefficient, the range would be closer, right? If the standard error is smaller. If standard error is like 5, that means your values, the upper and lower bounds would be farther away from the center, right? So in general, we would prefer a lower standard error, right? So and standard errors would differ, not standard error, confidence intervals would differ according to the significance level. If you want the significance level to be higher, like at 1%, the critical value for 1% is 2.57, right? And for 95% it's 1.96. So this is for 99% or 1% significance level. This is for 95% confidence interval or 5% significance level. So if your significance level is lower, the range of your confidence interval is wider, right? Because lower significance level means the critical value is bigger. If critical value is bigger, the range would be bigger, because it's minus 2.57 plus 2.57 times the standard error. So if you want to get a lower significance level, that means 99% confidence interval, the range will be wider than a 95% confidence interval. So, but we actually want a 95%, by that's the standard, all right? That's the golden standard. Here they have given a relationship between the confidence interval and the hypothesis test. So here, let's actually first look at an example, all right, before we discuss about this. So if you look at an example, this is the model of firm's R&D expenditure, and we have log of sales, we have profits as percentage of sales. We have a very big R square, right? My R square value was small, kind of. That was one of my criticisms in the paper. And the N value is also small here. It's only 32. So that's why the critical value is 0.45. It's not 1.96. When will it become 1.96? When the N value is large, then the T distribution behaves like a normal distribution. But since here N is small, the critical value is slightly bigger. All right. So they have constructed the confidence interval, the estimated coefficient of sale is 1.084, right? The estimated coefficient of sales, and then they the formula is plus and minus critical value times the standard error. Standard error is actually here in the parenthesis. So they have found their range to be from 0.961 to 1.21, right? And similarly for the profits as percentage of sales, they have found 0.0045 negative and positive 0.0479. Okay. Now let's look at the hypothesis about a linear combination of the parameters. Here, if you look at this equation, we are estimating the wage equation based on years of education at 2-year college or years of education at 4-year college, plus the work experience in the months in the workforce, right? You may ask that both are years of education. Isn't the variable multicollinear? What do you guys think? Because both are years of education. So for assumption, the multicollinearity assumption is saying that it should be no perfect collinearity. It doesn't say that if, let's say, the collinearity is like 70% between the years of education at college and years of education at university, then that's not a problem. Only if it is like perfectly multicollinear, or let's say like an almost 90% collinearity, then it's a problem in the model. Okay. And here if you see, the null hypothesis is actually they are testing the difference of beta 1 and beta 2. So they are testing the difference between those two. So, and they are saying that the null hypothesis is that the difference is equals to 0. They are saying that the years of education and at college, 2-year college, and years of education at 4-year college does not make any difference. Like if you attend a 4-year college or even if you attend a 2-year college, it doesn't have I mean the difference of wage, there is no difference of wage even if you attend a 2-year college or a 4-year college. In reality, we would expect that if you have a 4-year college degree, you will have a higher income, right? But they are testing that the null, in fact the null is testing that a 2-year college and a 4-year college, the years of education would have the same effect. In other words, beta 1 minus beta 2 is equals to 0. And the alternative is saying that beta 1 minus beta 2 is not equals to 0. Alright? So when they test these t-stat, on the top part is the difference, which is beta 1 hat minus beta 2 hat. Right? In fact, this t-stat is like this: beta 1 hat minus beta 2 hat minus 0. They didn't write the minus 0. And then standard error of beta 1 minus beta 2. Right? Is it clear? Because here when it was just a one case, let's say if we are only testing beta 1, we used to assume beta 1 minus 0 over the standard error of beta 1, right? But we didn't write the minus 0 because in general, what did I say? What's the golden rule? To assume the coefficient value as 0, right? When you are testing a hypothesis, you assume the golden rule is beta 1 equals to 0. But I also have told you guys that it is actually up to you if you assume it is equals to 0 or not. Because in this example, like a few minutes earlier, we have seen an example where they have assumed the null to be 1. So the null can be any values, right? But the convention is to use equals to 0, right? So that's only for a one variable case. So when they are choosing the difference in a 2 variable case, so we know that this is the difference, beta 1 hat minus beta 2 hat is the difference, and minus 0 means that there is no difference between those 2 years of education, right? And divided by the standard error of the both of this, because now there are 2 variables involved, right? So what's the problem with this? So impossible to compute the standard regression output, because now we have to calculate the standard error beta 1 hat minus beta 2 hat. So if it is that's the case, then it's actually root of the variance of beta 1 minus beta 2 hat. Okay, and if it is the case, then if you expand it, there should be minus 2 covariance of beta 1 hat minus beta 2 hat once we expand the formula. Alright, so because variance of beta 1 minus beta 2 would be variance of beta 1 plus variance of beta 2 minus 2 covariance of beta 1 beta 2, right? This is the formula which is actually inside this root. So in that case, this would be only true, I mean easier to calculate, if this term is equals to 0. Okay, So let's look at another equation like log of wage. So they have the junior college JC, they have the university and the experience. If there is a theta 1 in the original equation, what they can do is like they combine the beta 2 terms, the beta 2 JC and the beta 2 university together, and they have theta 1 JC. Okay. So in that case, we can assume the null hypothesis theta 1 equals to 0. So one way of actually fixing this is just testing theta 1 equals to 0 and theta 1 is not equals to 0. So if that is the case, then we would know that if theta 1 is equals to 0, that means junior college does not have any impact on the wage level. Alright? But in fact, they could not reject the null because no, the t-stat they found is 1.48, p-value is 0.07. We can reject the hypothesis at 10% level, but we cannot reject it at the 5% level. Right? So this method would work always for the single linear hypothesis. Right? So let me actually show you guys something from here. Okay, let me pause this. Let's say I want to calculate the college GPA, right? So college GPA is equals to number of hours you study then let's say, in fact, let's say GPA depends on the hours you put into study, right? So beta 0 plus beta 1 hours you study, right? HRS plus let's say beta 2 class attendance plus the error term. Okay, you can say that the hours of study and class attendance, aren't they multicollinear? They are not perfectly multicollinear, right? Because you also have to come to class to understand the material, and only at home you will be spending your time to study for your like a course, right? So they are not perfectly multicollinear. Now if someone is hypothesizing that beta 2 and beta 1 is equals to 0, what does it mean in this case? They are saying that attending class and just studying at home, there is no difference, right? Basically, if you are coming to class or if you are studying at home, they are saying there is no difference. Like this lecturer is useless. If I come to class, I try to understand the material, that doesn't help me. So you're saying that if I just study, if I come to class, then I don't, or you can interpret it another way, that if I come to class, I don't have to study at home. Okay, it can be, since I chose beta 2 as my first criteria, so if I come to class, I don't have to study at home. So that is the null hypothesis, right? So usually for t-stat, what do t-stat we calculate? We say beta 2 minus beta 1 minus no difference, which is the 0, right, divided by the standard error of beta 2 minus beta 1. But just let me ask you guys, is it easy to calculate the standard error beta 2 minus beta 1? Is it easier? No, because when you are calculating the standard error for beta 2 minus beta 1, we have to calculate the variance of beta 1 minus variance plus variance of beta 2 minus 2 covariance of beta 1 beta 2, right? This is the complicated part, calculating the minus 2 covariance of beta 1 beta 2. Just let's go back to our example. See, here also it is impossible to compute the standard regression output because we don't know these minus 2 covariance beta 1 beta 2. Alright, so alternative method is we choose a theta 1. Okay, so we can choose a theta 1 such that if we go back to our equation, you can say that instead of beta 1 in the hours of study, if we have something like theta 1 plus beta 2 hours of study, or in other words, if beta 1 is equals to theta 1 plus beta 2, right? So let me if beta 1 equals to theta 1 plus beta 2 beta 2, then if we just tested the null, that beta 1 theta 1 equals to 0 as the null, and the alternate is theta 1 is not equals to 0. Okay, that's an easier method of solving getting a precise estimate of the standard error. In fact, I am going to ask this question in the exam. Okay, so this question will be in the exam. So how to test, like reconstruct the model in order to get a correct estimate of the t-stat, right? So how do you do it? When we are trying to find the difference between beta 1 and beta 2, or beta 2 minus beta 1, you construct the beta 1 in such a form that you have theta 1 plus beta 2. You replace it. Okay, so if I rewrite it, if I rewrite the model now, let's use a different color. What would be the new model? GPA would be beta 0, beta 1 is theta 1 plus beta 2 HRS, hours of study, plus beta 2 class attendance. Right? Now you will have, so if I select this, so now you will have GPA equals to beta 0 plus theta 1 HRS plus beta 2 HRS. I just doing some algebra here, class attendance, right? And then, so if I rewrite this and take it up, so now theta 1 equals to 0 is my null, and alternative is theta 1 is not equals to 0. Right? Is it making sense? Now if theta 1 is equals to 0, that means hours of study does not have any effect on GPA. But if theta 1 hat is not equals to 0, that means hours of study does have effect on GPA. That means you just attending class won't help you pass the exam. You also have to work at home, right? So this would be in the video. Watch it, and this hypothesis I will test, like I'll ask in the final exam, like how do we correct. So I'll stop here today.